Hello and welcome to Lecture 16, Part 1 of Life in the Universe. We continue in our unit about telescopes and spacecraft. And in this video, we're actually going to learn about reflecting telescopes. But before we do that, since this is the first video of the lecture, I have an alien to tell you about, and there will be appropriate music in the description if you want to go listen to it. But here we have a scene from the movie Star Trek Into Darkness. It was the second of the three relatively recent, although I know going back more than a decade now, of the reboot or new timeline in the Star Trek universe. And in general, I'm not very fond of these films. They are enjoyable at one level, and there is some very good casting in it, but it's missing something that other, at least the TV versions of Star Trek had. The earlier movies were somewhat limited in that as well, but some of the deeper things from Star Trek are certainly missing from all the movies and certainly the more recent ones. But I still picked this picture because there is some excellent astrobiology here. And that is, if you notice all of the plant life in the swamp or whatever surrounding this alien temple, you notice that that foliage isn't green, it's red. And the thing is, on other planets with whose suns would have a different spectral energy distribution than our sun, other photosynthetic pigments other than chlorophyll would likely be most useful. And so we would expect analogs of plants on many other planets not to be green because they'd use something other than chlorophyll. So that is good. All right, now we ended the last lecture by looking at some of the problems encountered in a refracting telescope that limited the size of the objective lens, and this problem of chromatic aberration, that a refracting telescope can't focus all colors at the same place. And the way to get around these problems is don't use a refractor. Instead of a refractor, use a reflecting telescope or a reflector. I apologize for the of the words refractor and reflector. It's not my fault. All right, to help us kind of visualize, though, the first couple of things here, and we'll go back to the slideshow in a minute. We have a number of some small, the department owns 4 small reflecting telescopes of a model called ETX from Meade. And about 15 years ago, we had an adjunct who taught some of our astronomy who pointed out we could get them used fairly inexpensively, I think about $200 a piece. And so we got 4 of them, and then he would loan them out to students. And then a couple of them got trashed. So we don't loan them to students anymore. I apologize on behalf of your predecessors who took that privilege away from you by their misbehavior. But one advantage of having a trash telescope is you can take it apart and you can use some of the pieces of it for demo purposes. So this is the primary mirror from one of those telescopes. Now, mirrors, these modern mirrors, are typically made of glass with a reflective coating, usually aluminum, on one surface. And if you go look at your bathroom mirror, if you look carefully, you'll notice that aluminum coating is on the back surface of that glass. Now, for a flat mirror in your bathroom, that's a good place to have it. The glass is probably only a millimeter thick or so, light going through the glass to get to the reflecting surface and back won't make a big difference. And it also protects it being on the back. However, on astronomical mirrors like this one, the coating is usually on the front. You can see the glass is about a centimeter thick here, but that reflective coating is indeed on the front surface. And that means that the front surface of each mirror is the only surface that we have to worry about getting exactly the right shape. We don't care about the exact shape of the back surface. And even though we still want a good piece of glass, if we had a little imperfection, a little air bubble or something in it, it would have much less of an impact on a mirror than it would on a lens. Now, of course, that just saves trouble in how much work you need to do on each surface of a mirror versus a lens. But then remember, a size of a lens is limited by its weight because you can't support a lens from behind. You have to support it on the edges. but a mirror can be supported from behind. So that means that you can make a mirror much larger that will hold its shape than you can a lens. And we'll see in the next video in this lecture something about telescope size. Actually, even in this one, we'll see something about it, but we'll see even more in the next video. So let me get out of the share here. I'm back in the share. So you can see this here. Okay, so with a mirror, we only have one surface per mirror, and you can support the mirror from behind, so you make bigger mirrors. But then one thing that's probably at least as important is too, with mirrors, there's no chromatic aberration. As long as the light is going to reflect off that surface, it will always reflect at the same angle regardless of wavelength. So you can use the same telescope over a much wider range of wavelengths if it's a reflector than you can for a refractor. Now, maybe we should consider this another advantage of reflectors is that there are a number of different ways you can arrange the mirrors. So more diversity in reflectors. And you can even use multiple arrangements on the same telescope. So these are four of the most common arrangements. In all of these, the telescope is looking up. So these are the primary mirrors down here. Light's coming in from above. And on the left, we have the simplest arrangement for a reflecting telescope. Now, I'm not going to trace these straight lines very well, but I'll try something here. So the light comes in. See, I told you, reflects off the primary. And then the way I'm doing it, drunken light, then reflects back up to a focus here. And we call this prime focus. This is only practical on very large telescopes because your instrument, whatever you put here to detect the light, has to be small enough compared to the size of a telescope that it does not block too much light. Not very much anymore, but it used to be that it was reasonably common for the observer to physically be at prime focus when observing. And I'll show you a couple of pictures about that in a moment. And especially with photographic plates, it would be necessary to change plates between exposures. So that had to be done manually. The smallest telescope I know of where it was an option for the observer to physically be at prime focus is a 3-meter telescope at Lick Observatory in California. 3 meters is 120 inches. That's 10 feet in diameter. As I said, that's the smallest one I know of where the observer could be there. Probably a few that were smaller where you could have a smaller instrument there, but you only see that on big professional scopes. The second one is common on amateur telescopes. It's called Newtonian focus, named after some guy named Isaac Newton who invented it. So again, the light, which will be drunk in the way I try and trace it, reflects off the primary up to a small secondary mirror, small enough so that mirror and its supports don't block too much light, and then is brought out to a focus on the side here. This is commonly seen on amateur telescopes, but you don't see it often on professional scopes. I know of a couple where it was an option. And that's because a professional astronomer is going to want to mount some type of instrument right here. And if you do that, it's going to be up near the top of the tube, off the axis of the tube, and balancing that telescope will be quite problematic. So it's pretty rare to see on professional scopes. The third one, Cassegrain focus, is commonly seen on professional telescopes and on some of the higher end amateurs, where the light will come in and reflect off the primary mirror up to the secondary and then through a hole in the primary to a focus behind it, where any instrument you would mount there would be one close to the primary mirror, so close to where most of the weight's going to be. And then also at a minimum, it's on the axis of the telescope tube, so that makes balancing it easier. Now I'm going to get out of the share here for a moment. These MEAD ETX telescopes I'm telling you about are essentially Cassegrains with a slight adjustment. This is the main tube in the front of one of them. They actually have a lens, so they're kind of hybrids between reflectors and refractors. But this lens does, in this case, very little focusing. You can see there's not very much distortion when you look through the lens. And basically what the lens does is it does a little bit of a correction to minimize distortion at the edges of the field of view. Anyway, here's my primary mirror here. So if this was all put together, it would be put together something like this. So light comes in, gets a little tweak from the mirror. I mean, sorry, from the lens. The primary mirror does most of the focusing. So it reflects off the primary, back up the tube. And you can see on the tube there, the secondary mirror is stuck on the inside of the lens. And actually, that's kind of nice because lens being transparent, the support structure isn't blocking any light. I'll hold it up a little bit closer to the camera so you can see the reflection in the secondary mirror. Anyway, that sends it back down the tube. And this is a baffle to keep stray light from going through the hole in the primary. So the incoming light from the secondary would go through that hole and then be brought to a focus back behind it somewhere. All right, back to the share. Okay. This last one, Naismith focus, is increasingly common on the largest modern professional telescopes. So the light reflects off the primary up to a secondary and off to a third mirror, a tertiary mirror, which kind of like a Newtonian focus sends it out to the side, but lower, so it's closer to the center of mass of the telescope and positioned where actually you can send the light to something that would actually be mounted on the support structure of the telescope. And any instrument you mount there would then, balancing the tube itself wouldn't be a problem. And typically this mirror can rotate, so there'll be anywhere from 2 to 4 ports you can send the light to, so you can have multiple instruments on the telescope at the same time and switch between them in only a few minutes. Now, like I said, some reflectors can be used in multiple configurations. So the 200-inch telescope at Palomar, 5 meters if you want to think in meters, was the largest telescope in the world for about 30 years. And it can be used in 3 different configurations. Prime focus, where the light would reflect off the primary up to the secondary here. If you want, up to the prime focus there. If you want to use it at Cassegrain focus, the secondary mirror then folds into place. So the light, instead of getting the prime focus, would be sent down there. And then something similar to Naismith, there's a third mirror that could be put here that would send the light way out of the telescope. Typically use this if you need to send it to a very large instrument. There are some spectrographs that are the size of a room, so you might want to send it to that. That's called coude focus because it always comes out of a telescope in that direction. Depending on which way the tube is pointing, let's see here, where's my, very easy to lose track of where the little pin pointer is here. But this angle here varies the way your elbow bends. Coude is the French word for elbow. And so that's how it got that name. Here is a picture of that telescope opposed when looking down the barrel, as it were. And so you can see the primary mirror down here. It looks a lot like the one for the ETX. It's just bigger, even has the same kind of baffle on it. So if it could be used at prime focus, light would come in from the end we're looking in through, reflect off the primary up to here. And you can see the astronomer in there posing for the picture there. And then could be sent back down through the hole if you need to send it to Cassegrain focus. And then the tertiary mirror to send it to coude focus could be put in place if you're going to use it that way. Here is a picture of that Lick Observatory 3 meter, 120-inch telescope here on the left. Like I said, this is the smallest telescope I know of where the observer could physically be at the prime focus. And on the right picture, there's a person in the prime focus cage, and you can see it's a lot more crowded than the one for Palomar. Incidentally, the picture on the left was taken 1992 when I was a graduate student. I was out in California for a couple of weeks for a number of different meetings, including a long workshop at UC Santa Cruz. And anyway, we took a day away from that. My thesis advisor and I went up to see Lick Observatory. And so that's me right there. And the person standing next to me is Andrea Schweitzer, who is my academic half sister. So she was a graduate student at the time at the University of Wisconsin, and I was a University of Chicago grad student. My thesis advisor at Chicago, Kyle Cudworth, was also her thesis advisor. but because she was at a different institution, that's why I consider her my academic half-sister instead of academic sister. She has observed with the Palomar 200-inch at prime focus, and did so in collaboration with Kyle and with another academic half-sibling, Steve Majewski, who I don't have a picture of. But anyway, they have to take the weight of the observer into account if they're going to be at prime focus to balance the telescope. And you can see that Andrea is kind of on the petite size. Steve is, if I remember correctly, 6'5", and he's a really big, bulky guy. And I'm sure he probably weighs at least twice what Andrea did, or does. And so depending on which one of them was in the prime focus cage at any time, because only one person would go at a time, then I'd imagine the adjustment that had to be made between observers was probably the most that they might have ever had to make in any one particular group at Palomar. All right, this shows about how big, with current technology, it is practical to make a single piece mirror. As we'll see, if you make the mirror segmented, you can make it significantly bigger than this. But this is the primary mirror for a telescope known as Gemini North on top of Mauna Kea in Hawaii. This picture taken sometime before the mirror was installed, actually probably before it went to Hawaii. And anyway, I assume the technician here standing in the Cassegrain hole is an adult human, so that should give you the scale of it. In any event, this mirror is just a little over 8 meters in diameter. The classroom where we would teach this in person, if we could fit it through the door, this mirror would fit into that classroom, barely. There wouldn't be much room for us if we had it in there. Anyway, in the next video, we'll see how big you can make a segmented mirror telescope. But this is about around 8 meters, seems to be the current practical limit for a single piece of glass as to how big we can make it. All right, so this is the end of our video, and this is a picture I took last night while doing the dishes. My cat Floyd was, I think, hoping I was going to feed him some more. But sometimes when I've got the dishwasher open like this, he will crawl under there, light that, and that protects him somewhat from getting splashed with water after I've rinsed things and put them in the dishwasher. But he doesn't like that, so he usually doesn't stay there long. So anyway, so helping with dishes is maybe is our code for this video. And anyway, just one more video to do in this lecture, but it'll be taking a look at why we want big telescopes and how big at least visible light or optical telescopes, as we call them, are getting these days. So I don't have dishes to do before I do that video, but I need to go check what's in the dryer before so doing laundry while doing videos today. So anyway, till the next one.